Hello and welcome to Video Notes 6.2, where we're going to talk about determining whether a linear model is appropriate for some data. The only thing we have spoken of up to this point is using a linear regression model. You might notice that your calculator has also other regression models, which we actually do not get into at all in this course. We stick with the linear model, and when it's not appropriate, we think about maybe other ways to, leverage all of our linear model knowledge to help us out here. So this is going to be completely residing all along the idea and the concept of residuals. Reminder that residuals are going to be your actual y value subtracted by the predicted y value. Talked a little bit about this in the last notes, and so hopefully that isn't a like, what? So here's the thing, is that you can actually find all these individual residuals and you can plot them, okay? And that's going to be something called a residual plot that we'll talk about in a moment, because the main metric we've had so far is r and r squared, but it turns out neither of those things can really give it to you. So if you have an r squared really close to 1, it doesn't mean a linear model is necessarily the best fit. Or if your, again, r value is close to -1 or 1, then it doesn't mean that a linear model is in fact the best idea here. The decision of whether you have a truly linear association only comes from this idea of the residual plot. And the residual plot is another type of scatter plot in which we graph the residuals along the y's, and we keep the original x values for the association. So if we were looking at time along the x values, if we were looking at age of somebody along the x values, we keep that and our y values become the residuals, so this difference of actual and predicted. If you have a residual that is on the x-axis, then that is a residual of 0. So ideally, it would be great if you could get a lot of your residuals very close to the x-axis. It would mean that your predictions are not very far off. But it also allows us to see something else. When we plot all these different residuals, what we want to be looking for is no apparent pattern, sort of just a mess of randomly scattered points, equally distributed above and below the x-axis. That last part there is because if all of your residuals are above the x-axis, then that would indicate that, like, okay, well, maybe linear was okay, but obviously I'm like undershooting by quite a bit here. And same thing for the other side of it. So you want to see no pattern whatsoever in your residual plot, and you want it to just be a random scattered, sort of equally distributed above and below the x-axis. So if you do see that, then you can be pretty confident that your association is in fact linear. This means that the data is randomly scattered along your line of best fit with a mix of positive, negative residuals, and thus generally follows that line, follows that trend that you're coming up with. However, if you see a curve or some noticeable pattern, then a more accurate model might come from switching to a different function, or, as we'll find out on the backside here, re-expressing the data. That's going to be the move we make in this class, rather than going actually to a different function entirely. So why don't we go ahead and look at an example of this. So here we have the year and the candy sales in millions of dollars for the 2005 to 2015. And I've given you all the info here. Here's the table. There's the scatter plot. There's the residual plot. And so sometimes that is the case. You are just given all the info, and then thus you don't really need to go and touch the calculator. But I do want to show you how you can actually find these things using the table just given there. So why don't we go over to the calculator and remind ourselves of making a scatter plot, and then lastly, how do you make a residual plot in the calculator? Okay, so let's go ahead and review scatter plots on your calculator and then introduce residual plots on the calculator. So remember, always with this thing, the first step is to enter the data into your lists. So here I have all the different years in list 1 and the candy sales in list 2. If you haven't done that, pause and enter that data real quick. Otherwise, let's remind ourselves of how to make a scatter plot. So remember, we're going to go to second stat plot. And then from there, we're going to go ahead and go to that first one, turn this on, and it is the first option there, list 1, list 2, and we're going to hit zoom 9, and it gives us the scatter plot. It looks very similar to what we see on the paper there. Another quick reminder on some stuff is that you can also create the linear regression equation and graph it with it. So you can go stat, calc, we're going to go down to number 8, linreg a plus bx, list 1, list 2, and we can store this regression equation into one of our y equals menus, which I'm going to do by clicking vars. I'm going to click over to y vars, press enter for function, and just press enter for the first y1 and hit calculate. And there it is. It gives all the information. You can see that the r squared value given does match what's on your paper as well. And when we go back to the graph now, we still have our data, and then we have the linear regression line drawn in for us there. So if you wanted to, you could do a little dotted line along your scatter plot on your paper to sort of show where that looks. All right, but then how do you make a residual plot? So all of that hopefully was a bit review. How do you make a residual plot? Well, the great thing is when you calculate the regression model on your calculator also simultaneously creates all of the residuals individually and stores them into a list that has the appropriate name resid. So when we want to actually look at this, we can do that very easily. So what I'm going to do first is I'm going to go to y equals, and I'm going to clear this out just because I don't want that messing up anything I'm about to look at here. And then instead I'm going to hit second now, stat plot. And we're going to go back into the stat plot. We'll go to this first one here. And for our x list, remember, for residual plots, the x's don't change. It's the same x values as you were using before. So I'm going to leave it as list 1. For the y list, though, instead of list 2, I'm going to go find my residual list. To do that, I'm going to have to do this. I'm going to hit second, and I'm going to come to the stat button. Notice that's right above that it says list. That's just going to be the names of all the different lists we have. You might have some more in there. There's other different types of things your calculator can do that store information, specifically with the chi-squared values, actually. But you can see that we are interested in the 7th option. For me, might be a little bit further down for you if you don't see it on the screen. Keep arrowing down as long as you've been following along. If you ever don't see resid in there, it means that you have not run the linear regression yet. You need to make sure that you do that. So I'm going to hit enter, and it now makes the residuals my y values, which is what I like. And I'm going to hit zoom 9. And there is our residual plot. So look at the paper, look at this one. You can see that, yeah, that is in fact the residual plot on the paper as well. So now we need to make a conclusion about this. So what do we think about the scatter plot? Does it look roughly linear? What do we think about this residual plot? Does it have the different features we were looking for? Or is there something funky going on here? So let's go back and conclude about this data.
So after seeing what our calculator provided, I have now written down the following here. So I just sort of drew in sort of that regression line as a sketch there to sort of get an idea to let me sort of know, like, oh yeah, so the scatter plot looks roughly linear. And then more importantly, when I look at that residual plot, I don't see a clear pattern. It seems randomly scattered. It has about the same amount of points above and below. The distances above and below are about the same there as well. So that would mean, therefore, that's what those 3 dots there mean. Therefore, a linear model is appropriate. So if you need to pause and write that down, go ahead. If you've been following along, though, and you have that written down, it is time for you to go ahead and give the other one a try, which is going to give us the years between 1970 and 1984, looks like every other year, and the Republic National Bank mortgages in millions of dollars there. So the total value of mortgages at this particular bank for that year. So go ahead and take a moment and practice your calculator maneuvers, plug that stuff in, see if you can come up with the residual plot again on your own, and then what conclusions would you make? So here's what I said. So by looking at the scatter plot, it looked roughly linear. Maybe you had a keener eye than I did and noticed that it's had a bit of a curve to it, and that's totally okay as well. But that becomes even more apparent once you look over at the residual plot. You can see that it has this clear U shape or V shape in it, where all of the residuals are positive to start out with, swoop down into the negatives, and then return back up to the positives, not randomly scattered at all, very much a pattern. So the conclusion we would make here is that a linear model is not appropriate. So if you need to rewind and revisit any of that or look back at definitions, please do so. Otherwise, why don't you go ahead and jump down to this one and try this one on your own, which is to look at all these different residual plots. These are all residual plots, and I want you, and all fit with a linear model. All the data fit with a linear model here, remember. So I want you to decide whether you believe a linear model is appropriate or not. Put a star next to them, and then write a little blurb down below each one as to why you are starring it or not starring it. Because we'll come into class and talk about these sort of different things. Some of them are a little bit wonky and will be good discussion pieces for us. So be prepared to discuss and defend your answers in class. All right, let's move over to the backside now at this point. So as we've noticed, if your residual plot has a clear pattern, it means that a linear model is not appropriate here, even if your R squared is very close to 1. So even if your R squared is 0.99, like, hey, here we have an R squared on the second one of 0.9298. 93% of the variation in our Y values can be explained by the X values, okay? Mortgages values can be explained by the year. But, and that seems like a high number, but as we can see, that does not mean that a linear model is a good fit, okay? So here we have to look at the residual plot. So if it turns out we have something that is not linear, okay, then we don't just give up and go, well, I guess there's nothing I can do with that. Instead, what we would want to do is something called re-expressing the data. We would like to re-express the data to try to make it fit a linear model better. We don't just do it willy-nilly and be like, I'm going to move that point up and that point down. No, what we need to do is, kind of leverage our algebra skills here and think about, well, what if we did the same operation to all data points in the set? All the X values, all the Y values, maybe both, explanatory and or response. So you will never, ever need to do this on any of our tests or on the AP test, okay? You will not need to re-express the data yourself, but you will need to interact with equations that have already been re-expressed. So the most common forms of re-expression is to take the power of your X's or Y's, so like square everything, cube everything, or take the root, so like the square root, cube root, or the most common one, take the logarithm of one or both of the data sets there, okay? So let's go ahead and see an example where that has happened. So let's scroll down. With the way housing has grown since the 1970s, it's actually been via percent increase. And maybe you recall from previous math classes when we're dealing with an increase by a percentage, not a constant amount, that would be linear, but instead if it's by 2%, 3% every year, then that is going to be an exponential function. Props if you said it before me. So in order to straighten out an association that grows or decays in an exponential manner, the key here would be to sort of undo that exponential. Do you remember what undoes an exponential? So the logarithm will do that for us. So we'll take the logarithm of, in this particular case, just the Y values is all we're going to do here. And you can do this with any logarithms. The most common ones are the buttons on your calculator you can see. There's the log button, which is actually log base 10, if you remember.
Or there's the natural log button, which is the log base E. E is that irrational number 2.71828182845 and so on and so forth. So by taking any log, really, those are the most common ones, of all our y values here, it should straighten it out if in fact it was something that was kind of exponentially beforehand. So I went ahead and did that already in the table. You can see that the y's in our table are now called log of the variable from before here. And thus the units are a bit different. They're log of $1 million there. But I do want to show you how you can do this on your calculator. Even though you aren't going to be required to do this on a test, I still want to show you just so that way you can sort of see how you could do it if, like, there was an extra fun problem on a classwork or a homework where it's like, hey, fumble around, re-express. How could you do that quickly without making it feel tedious? Let's go over to the calculator and see how that is. So let's go ahead and see how our calculator can help us re-express. Remember, you never have to do this actually on a test, but perhaps in class we might choose something like this, and I want you to have this skill. So we're going to do this with the mortgage data. So if you haven't done so already, go to your lists and enter the small amount of mortgage data we have in there. You can see I have it already. And as we noticed, that the residual plot for this clearly has like a U-shaped pattern to it, okay? So I'm not gonna go through all the steps of making the residual plot. If you want to right now, go for it. Instead, I'm gonna show you how we can re-express the data quickly. So we believe that it is an exponential association, in fact. And so to undo the exponential, we're going to take the logarithm of all of the y values. So we could do that. You could come over here and you could type in log of 1.4 and hit enter, log of 2.3 and hit enter. But if you have a lot of data, that takes a long time. So your calculator actually can do all of it all at once very quickly if you actually go up to the name of the list, list 3 here, and type in the formula we want. We want to take log of everything in list 2. So we're going to hit second. And if you go down to the number 2 at the very bottom, you'll notice in blue it says L2, that's list 2. Close those parentheses and hit enter. And there you have it. It has taken every item in list 2, taken the logarithm, log base 10 of each of those, and it is now creating a new list for us in list 3 that is all of the log of these mortgage numbers, mortgage values. So let's go ahead and take a look at what the different plots look like for this one. So I'm gonna go second stat plot, and list 1 we're good with, but now I wanna look at the Y list of list 3. That's all the logs of everything in list 2. And we'll go zoom 9, and that looks a lot more linear than it did before. Yeah, very cool, very cool. So then now I'm gonna go ahead and go to the linear regression really quickly here. I'm gonna find the linear regression model for this. List 3 is what I want for my Y values here. I'm not gonna store anything, I'm just gonna hit calculate. And there is the equation. You'll notice that's on the paper. This matches what we have there. Look at that R squared value. That is pretty good. Remember, that's not the only thing that tells you that something could be has a strong linear association, but the fact that it is so close to 1 tells me it is very strong. So I'm feeling pretty good about that. And then now we're gonna go ahead and go back to our stat plot and look at the residual plots. Since I've ran the regression, it should have calculated all of the residuals for me and put them in a list where I can find by hitting second stat and arrowing down, or just hitting the number 7 for me in this case. And I'm gonna go zoom 9. And I can see that that is much, much better. That does not look like it has a U-shaped pattern. It's so few data points that I'm sure we could dig in and think that there's a pattern here, but there really is not a pattern at all. It looks like it's a good fit. Linear model now does seem very appropriate. So let's utilize this re-expressed equation now to help us with some predictions.
All right, so as we can see now, by doing that re-expression, we have this beautiful linear association now. And that's great because now we can talk about R squared like we did before, about how it explains the variability between our two different variables. It also means that we can sort of make predictions fairly simply, rather than digging into the crazy algebraic different functions. We can still make predictions. So the new equation that we would get is this. You'll notice that what we have going on here is that the left side of it, much like our variable in the table there, is not just the prediction of mortgages hat. Instead, it is log of mortgages hat, because that's what we did. We took the log of all of the values. So now we can use this equation model here to make predictions. There's only one thing though. We're going to need to undo this re-expression at the very end of it all, so that way we're back to the relevant units. Again, in the table, the units for the y's right now are log of millions of dollars, which is a bizarre unit to sort of think about. So we'd want to get back to just millions of dollars. We'll have to undo the logarithm. So why don't we go ahead and try an example like this and see what we can come up with. So what does our model predict for the value of Republic National Bank's mortgages were in 1978? Why don't you go ahead and take this as far as you can and then unpause the video and come back and see if you were able to figure it all the way out or if you need a little nudge to help you through it. All right, so hopefully you were able to get to at least this place, because you're just plugging in and sort of using your calculator to simplify that right side. But unlike previous times where it's like, great, and there's our answer, that's not the case this time, because we have not actually solved for the predicted y value in this case. All we have solved for so far is the log of the predicted y value. So in order to undo the logarithm, well, remember I said earlier that an exponential's inverse is the logarithm. Well, in this case, it's going to be the same going the other way. The inverse of a logarithm is the exponential with the same base. So this is a log base 10, which means in order to continue our work, what we're going to do is we are going to make both sides exponents with a base of 10. Here's what I mean by that. We're going to go 10 to the power of log of y hat is equal to 10 to the power of 0.748. I'm following that golden rule of algebra that as long as you do the same thing to both sides, you can't mess up the equation. I have just done that. I've made both sides of my equation just be exponents with bases of 10. I did that because 10 to the power of log base 10, those are inverses and undo each other, which will mean that my right side is just the predicted y value, y hat. And on the right side there, if you want to pause to try it into your calculator, you can, but spoilers, it is 5.6. 5.60, maybe there's some other decimal places there to it all. But since the values on the front side, because this is the same context as here, they just went to one decimal place, I decided to do the same thing. So let's go ahead and write out what this means really quickly. So in 1978, our model would predict mortgage values to be $5.6 million. Awesome. So there you go. So this is how you normally would have to deal with this type of re-expressed equation, is that the equation is given to you. Your brain should recognize like, oh, that has been re-expressed. The original scatter plot is not linear. And I have some extra steps when it comes to actually coming up with predictions for all of this. So the last thing I want you to do that you're going to do on your own here is to find and interpret
the residual. We got 5.6 is our predicted value here, 5.6 million. However, on the front side here, there is a data value for 1978. So you should go back to that, look at what it was, and then write down what is the residual and interpret what that means in the context. And then we're going to check that off along with the end of the front page as well when we're in class together. So make sure you get both of those done so you can get full credit on this video homework. We will see you in class.